Okay, let's have a look at question 4. So, thermodynamics first law given. A student incorrectly defines the terms as shown below. In each case, write the correct definition. So these are definitions that we have to know. It's worth remembering that this equation, this is just a conservation of energy equation. So delta U is the change in internal energy. So the total kind of energy contained in the vibrations of, or the kinetic energies of the particles in that substance. Q is heat transferred to the system, and W is work done by the system. And, you know, if you think of it in terms of energy, you can figure out whether it is work done by the system or on the system, and similarly you can figure out whether it is heat transferred to or from the system by just thinking of the effect of a positive value on delta U. You know, if we keep W as 0 if no work is done, and heat is transferred to the system, Q is positive, then delta U is positive. Similarly, if we keep Q at 0, no heat being transferred, if the system does some work, W is positive, and therefore delta U is negative. The energy in the system must decrease if the system has done some work. Part B, a cylinder with a leak-proof piston, so an absolutely classic setup, contains this many moles of an ideal gas, and the gas is taken through the following processes that result in changes in pressure and volume as shown. So we're going from A to B to C in a kind of clockwise direction around this loop. Always be careful with the units on these graphs. They are seldom in cubic meters and pascals. So in this case, it's 10 to the minus 3 cubic meters, and it's 10 to the 3 pascals. Confirm that the process A to B is isothermal. So let's have a look at A to B. In order to confirm this, the equation that we'll use is PV equals nRT, and N is constant. So constant temperature implies PV equals constant. So in general, I don't think you would have to write that in your exam. There's only 2 marks to be had here, but that's the principle that we're using. That's what we'll do. We won't bother to calculate temperature because we don't have to. We simply have to show that it is the same. So what I'll do is I will choose 3 points in the process. I would guard against simply doing this at the start and end at A and B, because if I find that PV is constant for A and B, that just shows that the final temperature and the initial temperature were the same. To show that the process took place at a constant temperature, I would be inclined to choose 3 points during the process. I'll call them I, and I. Points 1, 2, and 3. So let's try that then. At point I, PV equals, I should have checked, so 600 kilopascals and 0.4. 600 times 10 to the 3 multiplied by 0.4 times 10 to the minus 3. So our powers of 10 in fact cancel out. 0.4 times 600 is 240. At point 2 then, let's have a look, 400 and 0.6. Which also equals 240. And finally at point 3, 3 300 and 0.8. Which conveniently also gives 240. So PV constant, which implies constant temperature. Okay. I think, arguably I've played it a little on the safe side by choosing 3 points. Possibly 2 would be enough. But, better safe than sorry. I think I've guaranteed my 2 marks. Show that the work done during the process A to B is approximately 330 joules. Now notice the approximately here. In general, the principle that we're using here is that work done is equal to area beneath the graph. Now, the problem is, this is not a straight line. So if I draw in the straight line, if I were to use this trapezium, that's going to give me a number that is actually in this case significantly too high. So I think in this occasion I would be inclined to split this into perhaps 2 trapeziums. As with most questions that involve a graph, I would recommend just drawing onto the graph, to illustrate what it is that you're doing. So work done equals area under graph, and in this case I'm going to area A to 0.2 plus 0.2 to B. Area trapezium, so we'll use the formula for the area of the area of a trapezium, which is base times the mean of the 2 sides. So base length here to here, 0.3, and here to here, 0.6. Side lengths then for the first part, 800 and 400. So a half times 800 plus 400 multiplied by that base length of 0.3. And arguably I should be including my times 10 to the 3 and my times 10 to the minus 3, but those will cancel out. So I'm just going to make a statement here. I'm just going to write that at the side, and I'm not going to bother to include them. So that's the area from A to 0.2, and then I'm going to add the area from 0.2 to B. So my side lengths are 400 and 200. And the length of the base is 0.6. Giving me a total of, let's have a look here, that's 400. I'm going to throw it all in the calculator, not taking any chances. Oh, hang on. Say I'm not taking any chances, but I've managed to type the wrong thing into the calculator and come up with a fairly foolish looking answer there. So don't be like me, do better. What am I? I've completely lost my train of thought now. What's happening here? So that's 180. Oh my goodness, I don't know what is going on now. I'm doing my best to ruin this. 180 plus on this other side I've got also 180 equals 360 joules. Is that approximately 330? It's a little more. Joseph considers the whole process A to B to C to A. He calculates the heat flow into the system to be 150 joules. Grace disagrees and states that 150 joules of heat would flow out of the system. Determine if either Joseph or Grace is correct. When you see determine, typically that means do some physics, do some calculations, and find out. So from A to B to C to A. As we go around this system, as the gas expands, when we're compressing the gas, significantly less work is being done than the gas is doing as it expands, because it's expanding along this isothermal line from A to B. So that's substantially more work. So there is more work coming out of the system than going in. So there must be more heat going in than coming out. So I'm going to make that as a statement. More work done A to B, B to C. So net work done by system. Therefore, net heat must flow into system. The next step then is to calculate the amount of work being done from B to C. So the area from B to C, this is at 200 and goes from 1.2 to 0.3. That's from B to C. So that's 180 joules. Previously, the work done during A to B was 330. So the work done by gas equals 330. Therefore, 330 minus 180 equals 150 joules work done net. Therefore, 150 joules of heat must flow into system. And I'm just going to put at the end delta U equals 0 for complete cycle. Because we have to end up back where we started in a complete cycle. We have to end up at the same value of PV. Okay, that's it.